My name is Rowena McGowan, and I am the curator of the Museum of Healthcare. This is a re-recording of my March 6th talk, Seasickness, Exploring Disease on Boats. To tell you a little bit about the Museum of Healthcare, we are Canada's healthcare museum. We have about 30,000 artifacts related to the history of health and healthcare. About 15,000 of these artifacts are currently available to view online, and we're adding more all the time. I will be showing some of these artifacts in the talk. We're open year round, and our big picture goal is to provide perspective on the past in order to understand the present. I am the museum's curator. I have been published on medical history, and perhaps most relevantly to this talk, I do have a boating license, so I am part of the Great Lakes community. Before I begin the talk, I just want to give a quick content warning. This talk will cover subjects of death and disease of children, medical experimentation, poor medical consent, and animal experimentation. If any of these subjects may upset you, please move on from this talk and watch another piece in the Great Lakes Excellent Speaker Series. All right, I'm going to be telling a number of stories about the ways that boats and disease can intersect, and we're going to start with a local story. So we're going to talk about the 1847 typhus epidemic in Kingston. What is typhus? Typhus is a bacteria spread by fleas, lice, and mites. It causes fever, headaches, and rash, and there's typically about a 10 to 15% mortality rate, so it can be fatal. The typhus epidemic in Kingston specifically correlates with another major historical event, and that is the Irish potato famine. In brief, from 1845 to about 1849, crop failures led to widespread starvation in Ireland, and many Irish people left Ireland. About 90,000 immigrants sailed to Canada, and there was a nickname given to these ships. And unfortunately, it was not a happy nickname, so they were called coffin ships because they would frequently pull into the docks full of the dead and the dying. Unfortunately, ships do tend to be very close quarters. This is especially true of these ships, which were often overloaded. And close quarters are excellent places for diseases to spread. So if someone came on infected, it was very, very difficult to isolate them, and diseases would spread to other parts of the ship. This was true of typhus as well. So in 1847, about 50,000 immigrants come to Kingston, some of them infected with typhus. Kingston is not prepared to deal with this many patients. Kingston General Hospital had been established. The original building was built in 1835. You can see a sketch of it there. However, it had only been operating as a public hospital for 2 years, so 1845 was when it opened. This meant that they also established fever sheds along the waterfront in an attempt to house some of the patients, and some of them were taken in by local Kingstonians for care, which is a very compassionate act, but unfortunately did mean that local citizens were also infected with typhus. About 1,400 to 1,500 people passed during this epidemic, leading to a mass grave on Kingston General Hospital grounds. There was, however, a silver lining to this epidemic, which was that it led to a greater interest in public health, as well as a shift in the management of Kingston General Hospital. Up to this point, Kingston General Hospital had been largely volunteer. It was reliant on the work of people like local women, local doctors who donated their time and materials. But as a response to the 1847 typhus epidemic, the hospital management shifted from volunteer to professional management. And I'm going to show an item that relates to the typhus epidemic in Canada, but not in Kingston. So this is an Army Surgeons Regulation case, and it was used by a gentleman called Dr. R.G. Grassett. Dr. Grassett was a doctor in Toronto in 1847. Typhus was not just an issue in Kingston. The epidemic happened in other places, including Toronto. And unfortunately, there was some prejudice in the community against the people who had typhus, but Dr. Grassett chose to treat them and unfortunately lost his life in their service. However, his name may be familiar to you, and that's because there's actually now a park named after him in recognition of his service. So why was typhus such a big issue? Well, in 1847, they did not have germ theory. That was going to come a little later in the 19th century. So they were operating under theories such as four humors theory. So the idea that there were four humors in your body: black bile, yellow bile, phlegm, and blood, and they needed to be balanced to be healthy. Treatments would include dietary regulation as well as bloodletting. There was also miasma theory, the idea that what caused disease was bad air, and smelling bad air or breathing bad air was what would make people sick. Because they did not have germ theory, they did not have a lot of related concepts. So, for example, antisepsis, the idea of cleaning things, sanitizing things. You can see in the image to the right, there's the sac disinfestor, so something used to disinfect clothing and lice carrying typhus. This image is from the early 1900s. In 1847, they did not have the idea that things needed to be sterilized. They also did not have antibiotics. Even once you have the concept of sterilization, sanitization, keeping things clean, it still takes quite a while for people to figure out how to get infection out of the body once it has entered. So we have technically been using antibiotics for quite a while because people would do things like make poultices out of moldy bread, which is essentially using penicillin. But we really don't see the widespread usage of antibiotics until the mid-20th century. We see some very early experimentation in the very early 1900s. The date usually given for the discovery of penicillin is 1928 with Fleming, but we don't even get the word antibiotics until the 1940s, and we certainly don't get their widespread use. So antibiotics would certainly not have been available in 1847. And finally, vaccination, which also comes after germ theory with one major exception. So let's talk about that exception. The very first vaccine is against smallpox. Smallpox is a virus. Typically, it's going to have a 30% mortality rate, although that could be much higher in some situations and communities. It causes severe rashes and blistering. You can see an example of someone with smallpox on the right. And it often leads to severe scarring, and that is, of course, if you survive at all. And it was also the subject of the world's very first vaccine. Before the smallpox vaccine, we did have a related concept, the idea of variolation. So we had figured out that if you had smallpox once, you were unlikely to get it again. It provided protection against itself. So you would often see people being deliberately infected with smallpox in a way that would hopefully be less fatal. So things like through the skin was less likely to be fatal than orally. However, it was not a particularly reliable practice. In 1796, Edward Jenner, as the story goes, notices that dairymaids do not have scarring from smallpox. And as the story goes, he hypothesizes that this is because they have been infected with cowpox, which provides the same kind of protection. Certainly, it has been suggested that Jenner was, in fact, relying on folk knowledge, folk wisdom about the safety of dairymaids from smallpox, and certainly he would have been familiar with the concept of variolation. However, Jenner does an actual test. So he takes his gardener's 8-year-old son, James Phipps. He deliberately infects him with cowpox and then exposes him to smallpox. This is not something we recognize as medically ethical today. It is important, I think, to note that Jenner did take care of James Phipps for the rest of his life. He did recognize that James Phipps was important to him, but he also took advantage of a child that he had a great deal of power over. However, the vaccine does work. So James Phipps does not catch smallpox, and from that we get the concept of vaccination, and in fact we get the origin of the word vaccination because it comes from vaca, which means cow. And I'm going to show you a couple of vaccination tools from our collection. So this is a hollow point vaccination lancet. A lancet is essentially an early scalpel, so it's a small, delicate blade. Typically, lancets were going to be used for bloodletting, but this particular one has been specially designed in order to be used for vaccination. So it allows you to collect material from one person and transfer it to another. This is a Whitmore's automatic vaccinator. And here we have a scarificator. This is another bloodletting tool that was very popular in the 1700s, but it was later repurposed for vaccination. Now, once we have the concept of vaccination, throughout the 1800s, we do see widespread vaccination campaigns. However, there is an issue which is the preservation of the vaccine. So the question becomes, how do you transport smallpox vaccine before air travel or refrigeration? You're forced to use boats that will go on very long ocean journeys. And Spain had this issue, and they came up with an answer. And their answer was, you use orphans. So let me tell you about the Spanish Royal Philanthropic Expedition. So Spain would like to vaccinate the people in their colonies in order to protect them from smallpox, but they need to get the smallpox vaccine to those colonies. So they turned to Francisco Xavier de Balmes, who was already interested in vaccination. You can see he's done a translation there of a treatise on vaccination. And the philanthropic expedition relies on a simple principle, which is that the vaccine survives for about 12 days in a body. So what they end up doing is creating a chain of living vaccine carriers. So essentially you would infect your first person with cowpox. They would simply have cowpox. And then when they were at the very end of the disease, you would take material from them and infect the next person. So living bodies would be incubating the cowpox, which would be used in the smallpox vaccine. So the Spanish Royal Philanthropic Expedition, the bodies they use are the bodies of orphan boys. And you can see the ship Maria Pita departing in 1803. You'll see slightly different numbers for the original number of orphan boys that were used, but it would have been around 20. So they sail to Mexico. The story goes that by the time they arrived, the boys were almost completely healed from cowpox, and there was one blister on one boy, but they did manage to transport the vaccine. From there, they went to a number of other places, including Puerto Rico, the Canary Islands, the Philippines, South America, which is a continent, but they went to a number of countries in South America, as well as China. So it was a very broad expedition. They also picked up more children for a total of 62. Now, I have not found a lot from the children themselves about their perspective. This expedition can seem very upsetting to modern eyes. It is important to note, however, so we have the full understanding of it, that there would have been a benefit offered to these boys. They were orphans, they did not have a family, and so the idea was that people would be grateful to them for bringing the vaccine, and they would be adopted once they'd arrived at their destination. And as far as we know, that was true. They did get adopted. So even though this absolutely does not match our modern ideas of medical ethics, it is important to note that there would have been a material benefit at least offered to these orphans. As well, they would have been fairly well taken care of. It would not have been pleasant to have cowpox while on a ship crossing the ocean, but there were personnel such as nurses to take care of them because it was important to keep them healthy. Now, did this expedition work? It absolutely did. So about 300,000 people were vaccinated as part of this expedition. So we have talked about the idea of ships bringing disease. We have talked about the idea of ships transporting cures, transporting preventative methods. But what about if being on the ship is the thing that makes you sick? So let's talk about scurvy. So what is scurvy? Scurvy is caused by a lack of vitamin C in the body. It causes apathy, weakness, hemorrhaging, and most iconically, bleeding gums. And it can be fatal. However, it is quite easily cured with vitamin C containing foods, most sort of famously citrus fruits, things like lemons and oranges. Scurvy becomes a particular issue for sailors during intercontinental voyages. So it becomes very, very important during the sort of age of sail, the times when there were a lot of expeditions, the time of colonialism. We know this is quite damaging. For example, there's a story from the Dutch East Indies fleet. A boat went out with about 249 sailors on it, and when they returned 2 years later, because of scurvy, there were only 88 sailors left. So it could be incredibly damaging. Now, we do see reports of scurvy being cured. For example, in 1497, Vasco da Gama travels to Asia, is cured with citrus fruits. 1536, Jacques Cartier's expedition to the Americas is cured with spruce bark and leaves. And it's really important to note here that this is not Jacques Cartier being clever. This was the local indigenous peoples, their medical knowledge and their compassion treating these sailors. It is important to note, because often indigenous peoples' medical knowledge gets dismissed, that these were people who were very familiar with the curative properties of their local plants and choosing to help Cartier's expedition. 1598, the Dutch East Indies fleet carries lemon juice, horseradish, and scurvy grass, all things that could help treat scurvy. However, we do not see a widespread adoption of scurvy prevention methods, and particularly a lot of doctors on land who are writing about it are not very interested in or promoting this idea of fresh fruit, fresh food for scurvy. They don't really understand how to cure it. So enter Charles Lind. Charles Lind is interested in scurvy treatment, and in 1747, he holds one of the very first therapeutic trials, which leads to his 1753 treatise on the scurvy. So he tests 12 men with scurvy with 6 different treatments. So 2 men each are given one of these 6 treatments, and the treatments are cider, seawater, vitriol, which is sulfuric acid, vinegar, a mixture of garlic, mustard seed, radish root, and gum meal, which is a purgative. This was a very common scurvy treatment at the time. And finally, oranges and lemons. 2 men in particular did very well during this trial, and these were the men who were given oranges and lemons. And Lind writes up these results and suggests that sailors be given fruit juice. However, his work is not widely adopted. The Navy's Sick and Hurt Board refuses to supply sailors with fruit juice. This was short-sighted, but it is important to note that Lind's conclusions were problematic. Even though he had concluded that the oranges and lemons were helpful, they were not his primary concern during his treatise, and as well, it was not the most well-designed therapeutic trial. So, for example, he did not have a control group. He also did not standardize the patients he was working with, so they were all at different stages of scurvy. So it was not the most well-designed experiment. It takes until 1793. Thomas Trotter and Gilbert Blaine advocate for the use of lemon juice in the British Navy, and this is adopted. So the British Navy's not getting scurvy anymore. That means we've got it, right? We've got it sorted out. Not yet. So in 1845, the governor of Bermuda suggests switching to lime juice. There's a lot of lime plantations available. And in 1860, we see a wholesale switch to limes in the British Navy, which gives the British Navy the nickname that is used for British people even today sometimes, limeys. Unfortunately, this leads to a wide-scale reoccurrence of scurvy. Why did this happen? First of all, limes contain less vitamin C in general. As well, it's certainly been suggested that the preservation methods, things like the copper piping that they were using, was actually removing a lot of vitamin C from the lime juice. So why couldn't the Navy seem to figure this out? Why couldn't they figure scurvy out? Why couldn't they figure out an effective treatment? Well, what if we actually know about scurvy? We knew that lemon juice is good for scurvy. We have figured that out. Lime juice, maybe not good. Don't really know why, but lime juice bad maybe. Vegetables in general seem to be good. Fresh vegetables, good for scurvy. Fresh meat also, there's a bit of a question mark. We think maybe, certainly now we know it's true. So for example, the Inuit, a lot of Inuit people get a lot of their vitamin C traditionally from fresh meat. We don't know what causes scurvy. We think a lot of people think it's something to do with ptomaine, that it is some sort of food poisoning thing, that it's related to sort of canned foods. Once we get germ theory, we start thinking it's maybe a bacteria. That makes sense. Bacteria causes disease. There's ideas about acid. We know that lemon juice is acidic. We know that lemon juice is good for scurvy. So we start to get these ideas that maybe it's something to do with the acid. We need more acid in our diet, and that's what causes scurvy. What we do not have is the concept of a vitamin, and we do not therefore have the concept of a vitamin deficiency. That is not going to happen until the 20th century. In 1907, Axel Holst and Theodore Froelich begin to do scurvy experiments, and they get very, very, very lucky. Let me tell you something about biology. So most animals can, in fact, make their own vitamin C in their bodies. So for example, if you feed your cat solely on kibble, your cat does not get scurvy because it can manufacture its own vitamin C. Humans cannot. This is somewhat rare. There is another animal that cannot make vitamin C in its own body, and it's guinea pigs. So Holst and Froelich got very, very lucky that they happened to use one of the few animals that they could have that actually could potentially get scurvy. So they start to get this idea that it's clearly some sort of nutrient deficiency. Something's going on here. In 1912, vitamins are named by Casimir Funk, vitalamines. So now we have a concept that vitamins are something that exist and that the body needs them. And we do see this idea starting to permeate. So for example, Ernest Shackleton's Imperial Transatlantic Expedition from 1914 to 1917. One of the gentlemen on this ship, John Lachlan Cope, is a biologist, and in his writings, he actually talks about scurvy and directly relates it to the idea of vitamins. So we're starting to see this idea be adopted, although it's very new. We hit 1928, the discovery of vitamin C, specifically by Albert Svent-Gorgi. So we have already had the concept of vitamins. Now we have found the specific vitamin. 1932, Charles Glenn King isolates vitamin C, and in 1933, Norman Hayworth deduces its chemical structure. Now we know exactly what vitamin C is. That leads us to be able to do things like create supplements, which you can see on the right. You'll notice also that the supplement is not labeled vitamin C, it's labeled ascorbic acid, which is a common alternate way of referring to vitamin C. And I actually want to talk for a second about ascorbic acid. So let's break it apart and look at what it actually means. So ascorbic acid. A means not or anti. So, asepsis, we've already talked about that. Ascorbic means scurvy. So we discovered vitamin C and we immediately named it anti-scurvy acid. So we have now talked about carrying disease, carrying treatments, and scurvy. We have not actually talked about what this talk is named after. We've not talked about seasickness. So let's talk about seasickness. Seasickness is a form of motion sickness. It's caused by a conflict in the balance mechanism located in the inner ear. It is not fatal, but it is a very miserable experience. I'm subject to seasickness myself, despite my boating license. So I have a lot of sympathy for people suffering from seasickness. Now, before I move on, a quick thank you to Roger Litweiler, who has been heavily involved in the Great Lakes Museum, and I'm pulling a lot from his research in this next segment. So did you know that there is a Canadian connection to seasickness? And it's Charles Best, his name may be familiar to you. He was a Canadian physiologist, and he is the best in Banting and Best. He is a co-discoverer of insulin. You can see him there with Banting and one of the dogs they experimented on. He was a methodical biochemist who made several important advancements in medicine, as well as the insulin, for example. He was also instrumental in heparin, the key to open heart surgery. Now, Best joins the Navy during the Second World War, and in 1940 becomes the director of the Medical Research Unit. The naval safety is very important to him. He makes advances in life jacket and night vision technology. He also sails on the HMCS Venture. The Venture is a model of ship that is particularly subject to waves, and a lot of people did get seasick on it. From this, Best realizes that seasickness can be quite debilitating for sailors, and he decides to do something about it. So he begins to develop seasickness pills. So he goes to focusing on his lab work at the HMSC York, and he develops a hanging seat for testing. So essentially, this is a seat on a system of pulleys that you can yank the person in the seat around to make them very sick. A number of sailors did participate in this testing. They were generally pretty interested in being involved because they would like some seasickness pills. And it had a joking name, which was the HMSC Mal de Mer, or the HMS. Essentially, they called it the seasickness boat. And Best is successful. He creates the Royal Canadian Navy Seasickness Remedy, which is right here. You can see on the screen, we have a bottle in our collection. All right, that's all I have for you today. Thank you so much. You can see the museum's contact info here if you're interested in learning more about healthcare, as well as some further reading. Thank you.